All right, so now I want to just kind of review all things arc length when we're dealing with vector valued functions. So I'm going to use the function vector r is sine 4t, cosine 4t, and 3t. Those are the three components. I've graphed it using GeoGebra, so you can see it's a circular helix. And we're going to go through all things arc length. Okay, so first thing we're going to do is we're just going to practice evaluating our vector valued function. So let's find r of 0, r of pi halves, and r of 3 pi. And then we're going to see if we can find all these places over here on our graph. Okay, so r of 0, notice, right, these are all vectors. I'm just evaluating it, right, at particular values of t. So sine of 0, so 4 times 0, sine of 0 is 0. Cosine of 0 is 1, and 3 times 0 is 0. Okay. So our first vector at 0, this is, right, pointing at 0, 1, 0. So starting from the origin, it's pointing out to this point right here. Right, so you'll notice that that 1 is in the y position. So now I know, right, this is my y-axis and my x-axis, and z is going up. Okay, pi halves. So plugging in pi halves, I'm going to have the sine of 2 pi. Okay, the sine of 2 pi. Oh, that's also 0. Cosine of 2 pi. Oh, shucks, that's also 1. I'm kind of at the same spot, aren't I? Oh, here's a different one. 3 pi halves. So what is that, like 4.5 or something? So I'm kind of just above this graph, but I'm up. Right, I'm up a little bit. I'm up closer to, right, 4.5, which is probably right this point over here. Okay, the last one here that we'll do. Oh my gosh, I'm still in that same spot. I should have picked a different t value. Okay, so r at 3 pi. So that's going to be the sine of 12 pi. So right, those even pi's for sine, right, if you use your unit circle, even pi's, right, are ending up on the x-axis. So the sine value is going to be 0. Cosine value is going to be 1. And then the only thing that's really changing here is my z, and it's just going to get really, really big to 9 pi. I was thinking it's about 27. Okay, so that point there, that way. So about 27, oh gosh, even off my graph. So it's another one of those loops up here. All right, so let's go ahead and find our velocity. So the velocity, remember, v of t is just the first derivative of our position function. So just writing that in function notation, right, as our vector. So v of t is going to be, so remember your chain rule. Gosh, let's get this so everybody can see. So the derivative of sine is cosine times the derivative of what's inside. So we'll get 4 cosine 4t. And then we'll get, so cosine goes to negative sine. So negative 4 sine 4t. And then the derivative of 3t is just a 3. Okay, well, that's interesting. Okay, so here we go. So the velocity at 0. So cosine of 0 is 1 times 4 is 4. Sine of 0 is 0 times negative 4 is still 0. 3 is a constant, right? Just 3. So what does that mean exactly? Right? So, right, we're starting here. So here's where t equals 0. Okay. The position function is going from the origin out to that point. Okay, that makes sense. The velocity, so the direction that this particle is moving, so if this is the right path of a particle at this particular time, it's moving 4 units in the x direction, nothing in the y, and then 3 units up in the z. So it's coming out this direction right from that point. Cool. V at pi halves. So at pi halves, that makes that 2 pi. So this part here is still 1, right? So it's still 4 in the x direction. This is what keeps it going in a circle, right? 0, 3. Hey, guess what this next one's going to be? Yeah, exactly. So we've taken out, right, that increase in our position, right? Because it's moving up at a constant rate, right, of 3. That's the velocity is moving upward each time. Okay. What if we would have done, okay, just so that they're not all the same, I'm going to toss in a whole new one here. Let's just find v at pi fourths, just to mix things up. Okay? So v at pi fourths. So plugging in a pi fourths here, right, I'll get 4 times pi fourths. That'll just be pi. Cosine of pi is negative 1, right? Cosine of pi is negative 1 times 4, so it's negative 4. So now I have a negative x velocity there. Okay, we're going to have to keep that in mind. Sine at pi, okay, that's still 0. Interesting. By the way, the y velocity is not always 0, right? You can tell sometimes it is, right, moving in the y direction, back or forth. We're just kind of finding ourselves on those, the side values there. And then 3 is the constant. Okay. So what was our position at pi fourths? Can we figure that out? Can we figure out our position at pi fourths? I know I'm not doing arc length anymore, am I? I kind of got off on a tangent here. So r at pi fourths, so I have the sine of pi, that's 0. So 0 in the x direction. Cosine of pi, negative 1. And then this is going to be 3 pi fourths. So it's at 9 fourths, just past 2-ish. So I'm negative 1 in the y direction. So I'm kind of back over here, right? So just above, I have 0 in the x direction. So I'm back and up, right? So there's my position. And then at that point, my velocity is changing, right? Well, my position is changing. My velocity as I'm headed backwards, back this direction and up. Okay. All right. Now, if we want to find the speed, so speed is just the magnitude of velocity, right? So you notice our velocity is a vector. That means it has a magnitude and a direction. If somebody asks you for the speed, you just want to know how fast. I don't care what direction you're going. Just tell me how fast you're going, right? So the speed at 0, well, those are all going to be the same, aren't they? Because they all have the same velocity vector. All of those are going to be the same. Oh my gosh. Okay. So we're just going to find that once. And then we're going to find a place where the speed is different. You think we can? I don't know. Let's see. V of 3 pi. And then finally v at pi fourths. Oh my gosh. The fact that we have all of those being exactly the same because they have the same velocity vector. So when I find the magnitude, so square root 4 squared, 0 squared, and 3 squared, 5, makes me a little nervous. It makes me think maybe it's a constant speed. Shall we see? Let's just try to pick some random value. So not something ending in a 4. Let's do something ending in a 3. Okay? So let's do, let's find the v at pi thirds. Just to see. Okay. Oh gosh, I might need a calculator here. Okay, I'm going to pause and evaluate all of those so that it's not troublesome. You can grab your calculators and do the same. Actually, I'm going to do mine with a unit circle because that's how I am, but I don't want to bore you with it. Okay, so I'm going to pause and I'll be right back. Okay, so I found out that the velocity at pi thirds, I've got negative 2, 2 roots of 3, and 3, right? That constant z version of z component of our velocity. Okay, what's the speed? So I've got a 4. I've got a 4 times 3. 4 times 3 is 12. And I've got a 9. 16 and 5. Oh my gosh, it is. It's a constant 5. Okay. I think that has something to do with it being a circle, right? Okay. But it did have a different velocity vector at least. So you can see that, right, not all of our velocities are exactly the same, just that C component in this case. All right, so arc length, finally, right? 11 minutes in, I said I'd tell you about arc length. Here we go. So how do we find the arc length again? All right, so we want to find r prime of t, find that length, velocity, right? And then we're going to integrate that from 0 to 3 pi. With respect to t. So that would tell us, and unfortunately, right, 3 pi goes off our graph here, but that tells us how far you're going to walk up this spiral staircase, right, if you walk the whole distance. All right, so we actually have, right, this is just, right, our velocity. I've left off my vector stuff. It was getting a little too crowded in there. So we're going to integrate from 0 to 3 pi, our velocity vector, or the length, the length of our velocity vector. So squaring, so 16 cosine squared, 4t, squaring, that'll make that a positive again, 16 sine squared, 4t. I thought I could fit, it's all going to fit but my dt, and then squaring plus 4, or plus 9 dt. So arc length S equals 0 to 3 pi. So I have 16 cosine squared 4t plus 16 sine squared 4t. So a little bit of trig and a little bit of algebra. Factor out the 16. You'll get a cosine squared plus a sine squared. Same argument. That's a 1. So these two terms here that I'm going to squiggle underneath, that's a 1. Plus 9. dt, so I'm integrating square root of 10 dt, so I'm going to get square root of 10t between 0 and 3 pi. So the arc length, right, the distance you're going to walk is 3 pi times the square root of 10, right, in whatever units you've got. Okay, how about the arc length function? How do we find the arc length function? First off, remember, what does an arc length function tell us? Right. So it's a function, s of t, that's going to tell us how far we've walked along our path at any given time t. Okay. So essentially, we kind of use this arc length idea here, but we reparameterize and then we integrate. So s of t is the integral from, right, some value a up to t of the length of the derivative of u with respect to u. Okay, so I'm just going to grab my little, right, derivative up here that's in terms of t, reparameterize it in terms of u, and then do my integral. Right, so s of t equals the integral from a to t of, what do I have there? The square root of 10 du. So, right, even if I put u's in here where the t's were, see where I'm pointing? Even if those were u's, I still have 16 cosine squared for u plus 16 sine squared for u. Right, the u's go away. I just get a 16 out there. Oh, shuckaroonies. Did you guys catch that? I just caught it now looking back. I wrote a 1 there. It was supposed to be a 16. Okay, I'm going to fix it now. Sorry about that. 16 plus 9... square root of 25, that's just a 5. So 5 times t times 5. So I really meant that to be 15 pi. Thank you for those of you who caught that before. I'm sorry I didn't hear you hollering at me. I eventually caught it. So, okay, I'll fix that down here. Where's my tape? Okay. So integrate, now that I'm actually going to do it, right? So I'm really going to integrate 5 du from, right, a to t. So my s of t is just going to be 5t, right? We'll choose a to be 0. So there's my arc length function. So, right, if you know when you're interested, you can just find out how far you've traveled by multiplying 5 times how long you've been walking. Okay. Distance equals rate times time. We have a constant rate, right, of 5. And then, right, time, how long you've been walking. And lastly, finding that arc length parameterization. So this is where we want, right, this is a specific parameterization of R so that your velocity is a constant 1. So velocity always equals 1. So let's go ahead and go back up. Okay, so we're going to grab our arc length function. So I'm kind of building off of things I have. Sorry. So you grab your arc length function. S is equal to 5 times t. We solve this for t. So t equals, oh gosh, s's and 5s, I'm sorry. S over 5. So my s's are going to change to being cursive s's so they don't try to become 5s. And then the arc length parameterization is we just rewrite R as a function, right, of S. So I'm going to replace the T's all the way back up here in my R function. I'm going to replace all of those T's with this expression we have, right, that has S's in it. So the sign of 4t, but t is now being played by S over 5. So 4s over 5 cosine 4s over 5 and 3 times s over 5. Okay? So what you'll see, got a vector, if you do this computation, right, if you find the speed of this, right, particular parameterization of R, this will equal 1 for all values of S.